All right, welcome to the Aztec Protocol webinar series video on transaction execution. In this video, we're going to do a brief intro into what Aztec is. We're going to go over the transaction phases that are involved with every transaction, go over local execution process, what the transaction object is, and then public execution. So to kick off, what is Aztec? Very simply, Aztec is a privacy-first rollup on Ethereum. Being privacy first means that we have private and public execution. This means that we'd have private and public state on the Aztec network. So we'll go into a bit more about what that looks like in this presentation. So, as I mentioned, Aztec is a rollup on Ethereum. So there are multiple actors that make this blockchain work. First of all is the user devices at the bottom of the screen here. They send transactions to rollup sequencers that sequence transactions just like many other rollups on Ethereum, and then those are settled on Ethereum nodes themselves. For maximum privacy, users have to be able to execute all transactions on their devices, because if you're passing secret information into Aztec contracts and as part of Aztec transactions, you can't share that secret information with anybody. So it must be executed locally on user devices. This private information, like contract functions and states of contracts, is set up as a UTXO-based state tree. And what actually goes into the tree are commitments to data. So users compute private contract state changes. They pass required information to sequencers, which will process and verify these private state updates, updating private state trees accordingly. But then these sequencers also process public transactions. When sequencers process public transactions, this is very similar to what happens in other rollups, and other blockchain networks, where remote computers are just updating public account-based state trees. This is transparent information that everybody sees. This is not private information. And as a rollup, Aztec publishes these updates to Ethereum, and these updates are verified, and they're verified with a zero-knowledge proof to basically validate that all of the protocol rules have been followed. And if you guys are familiar with the Aztec Connect, the Aztec network also has functionality similar to Aztec Connect, where transactions from the layer 2 can interact with Ethereum layer 1 as well. We'll go over that in a future video as well. So getting into transaction phases. So what is a transaction? How do we define a transaction on the Aztec network? Very simply, it's just any state change to the network. If any of the private state trees are updated, there's a transaction on the network. If any public information on the network changes, there's a transaction to the network. So there are 3 distinct phases to each transaction. There's a validation and fee preparation phase, there's the actual execution of the transaction, and then there's fee distribution. So all of these phases occur within the same transaction, and they ultimately result in 2 sets of public inputs being emitted from the private kernel circuits for private transactions. So the public inputs that are emitted from private transactions are the proofs of correct execution, the commitments to any new data, as well as nullifiers that invalidate any old data that's been updated. So because we have like application logic that may be executed as part of this, as well as transaction fees that need to be paid, that's why there's 2 sets of public inputs, one set for the actual application logic, called that the app payload, and then another for the fees that get paid to the sequencer. So in the first phase, validation and fee preparation, these can be private or public, say with execution, private or public, but the fee distribution must be public. So transaction fee distribution is public to sequencers. Fee distribution must be public because sequencers handle paying out transaction fees. Private functions happen locally, so the sequencer fee payments must happen during public execution. The sequencer will have agency over which contract methods they are willing to accept for execution in these phases, so they have visibility over the arguments passed to them. That's why this must be public. And then the sequencers can choose to accept transaction based on this information. They're following rules that they define. Similar to Ethereum in terms of how transaction fees are paid when transactions revert, with validation and fee preparation in the first phase and the fee distribution in the third phase, these state changes are only reverted if the fee preparation or distribution failed, state execution changes over if any component fails. This is basically saying that you pay transaction fees regardless of what part of your transaction fails, unless the fee validation and preparation and fee distribution fail. So you're paying transaction fees for failed execution logic, for failed application logic. So digging into local execution. When users are creating transaction execution requests, they send a request to software running on their device called the private execution environment. This is a piece of software that will simulate and generate the proofs for any private transactions. So users are sending this transaction execution request to their private execution environment. We abbreviate that with PXE, and we call it the PXE. But the transaction execution request includes these components. So there's the origin, which is the address of the contract that the transaction's coming from. It's typically an account contract, but it doesn't have to be. There's a function selector, which is the entry point of that origin contract. In our account contracts, we typically just call that entry point. There's the first call arguments hash, which is the hash of the arguments going into that first function call in the origin contract. There's a transaction context, which includes things like the transaction type, chain ID, protocol version. The transaction type can be standard or fee paying or fee rebate. There's also the arguments of all of the function calls that will be part of this transaction. So a transaction may call several functions or maybe nested function calls. If there's any additional inputs required, those will go in the transaction execution request. It's used by the PXE and the nested function calls. And then any authorization witnesses, which are used by the PXE to determine if a specified contract or function is authorized. You can think of this similar to approvals in Ethereum, but they're much more flexible and easier to use from a user perspective. The transaction hash is generated from the transaction execution request, and it just includes the origin, the function selector, the transaction context, and the first call arguments hash. So you can get the transaction hash, which will be the transaction ID. So how does this private execution work? The PXE will simulate the transaction on the user device and creates a state diff. So this happens client-side on user devices, and this simulation will return a transaction object that is identified by the transaction hash. Any failed assertions and transaction outputs and side effects can be returned to the user to review to make sure that this transaction is actually doing what they think it should be doing, and then users can approve. But this step would be up to like a wallet implementing it. So once this is simulated and the user approves, like verifies that they want to do it, the PXE will actually generate a proof on the user's device. Typically we simulate first because generating a proof will take a bit more time. It's much faster to simulate. So we want to simulate it, make sure it will be successful, and then users can generate a proof, which will take some time. They generate a proof on their device following the rules of the VM and verify that the state diff is correct. The users will send the state diff and the transaction proof to the network, to the sequencers for inclusion in a block, and then the sequencer will actually generate a block, roll up all the updates recursively into one proof, which will be submitted to Ethereum and verified in the smart contract there. So I mentioned after the PXE simulation step returns a transaction object. This includes some important data that will be sent to the network. Actually, the PXE will generate the transaction object after it generates the proof. So it goes through simulation, then proving, and returns the transaction object. This transaction object includes data, which are the public inputs of the last iteration of the kernel circuit. All of the function execution is recursively verified as the PXE generates the proof. So it only needs to provide the inputs for the last iteration. And these public inputs include the note hashes, which are the commitments to the private data, the nullifiers for any data that has been consumed in the transaction, and any L2 to L1 messages. It also includes the proof, which will be a honk proof. Honk is the cryptographic system that we're building at Aztec Labs that will be used to verify all zero-knowledge proofs on the network. So the proof is a honk proof of the last iteration of the private kernel circuit for the transaction. Any public function calls that this transaction is requesting on the network will be passed as part of the transaction object, so the sequencer can execute those public function calls and do the corresponding state updates. And then any encrypted and unencrypted logs emitted by the transaction are also included for the sequencer to publish to Ethereum for data availability. So I talked a bit about how public execution looks as part of the transaction, but digging into more detail, there's a number of transaction validity conditions that the sequencer will check to make sure that the transaction is actually valid. Some of them here are the proof being submitted as part of the transaction is actually valid. It should be checked against the protocol verification key for the provided version of the Aztec network. Should check that there are no duplicate nullifiers. No nullifier in the transaction data should already be in the nullifier tree. This prevents any double spending. There should be no pending private function calls, and that call stack should be empty. All historic data should be valid, and block header tree roots must match tree roots of the historic block. We need to make sure the max block number is not exceeded. The block height must be less than the max block number specified in the transaction data. We use this when we are reading shared mutable variables that can be read in private or public state, and we must check that preimages must match commitments. So logs, contracts, and include public function call commitments must match the preimages that have been specified. There are some additional things that we need to make sure the transaction follows. One of them is that the transaction is within our constraints. These constraints will likely change as we integrate our cryptography into our network. Right now, the sandbox is mocking a lot of our cryptography, so we just have hard-coded commitments. Right now, it's 64 commitments in a transaction, 16 commitments in a call, 4 nested function calls in a transaction. But these will likely change. And we need to check that the call stack hash matches. What is public execution? Public execution is the transaction object that I mentioned before, which includes the proof. So the user sends the transaction object and signature to the P2P network via node. In Aztec, it doesn't strictly need to be a signature. Our account contracts right now use signatures to verify authorization for use of an account contract, but developers can write account contracts that use any sort of valid proof to authorize access to a contract. And the sequencer is going to order the transaction, pick transactions from the pool and order them into a block, and then execute the corresponding state updates with those transactions. So on the sequencer, public calls are run by the sequencer and operate on the latest state. Sequencers are running Aztec bytecode. Public functions in the Aztec network are specified in AVM or Aztec virtual machine bytecode, which is executed and proven in the Aztec virtual machine. Public calls run on the AVM. The public kernel circuit aggregates calls and produces a proof. So the sequencer is responsible for proving correct execution of public function calls. It's likely going to look like the sequencer requesting these proofs are generated from a prover network or some third party that are generating proofs for them. But the idea is every transaction has a proof, and these are recursively aggregated into one final proof. That final proof of correct public state updates for the entire block is included and published to Ethereum. The sequencer also processes transactions that may revert for some reason. Transactions may revert due to failed assertions, running out of gas, calling non-existent functions, or other reasons, but users still have to pay transaction fees for transactions that revert. When a transaction reverts, the execution halts, the side effects are discarded, but the fees are still paid to the sequencer. I hope this was helpful. You can read more in our docs at docs.aztec.network. Follow us on X at Aztec Network, and we will be coming out with more protocol webinar videos soon.